Okay. I thought that this conference would be a good place to talk about, throw some ideas out about what kind of databases are people going to be using in 2020. Other than, of course, the legacy databases that they've been stuck on and haven't upgraded since now. So in terms of what kind of databases are we expecting that people are going to want in the future? Because we went through this sort of, we've gone through an interesting history recently where this sort of period where there were actually, if you go from, say,
the 1600s?
Yeah, well, we're going to stick to databases that exist in computers. So if you go from, like 1960 or so to 1995, you actually see a bunch of different kinds of databases. Because like from the first early ones that we had, started out with your hierarchical and network.
Actually, it started out with this flat file.
It started out with flat file databases.
ISAM.
Yeah. So it went from.
You started flat file on
Yep.
tape. And punch cards.
Yep. Yes, my father was a direct contributor to the Y2K problem. So yeah, and then our hierarchical and network, and then your multi-value databases, plus some other sort of random exotic databases for different purposes and that sort of thing. And this is sort of presented, and then finally coming sort of latest was relational.
I would put associative array in there also.
What?
Associative array.
Right. Well, actually, that was my, God, where did Colin go? That was my other idea for Keynote. So we'll talk to you later.
Yeah.
Talk to you about that later. And this is presented, if you look at this from the textbook, this is presented as a progression of database types, which is absolutely not how it, some things came first and other things came later, but it's absolutely not how it happened. People are still using some of these kinds of databases today, but they're in very sort of niche, unchangeable application stuff. For most of these multi-value databases, 1965, PIC and its descendants are still in significant heavy use today.
PIC is still
around? Yeah, actually. There's some applications that still run on PIC. There's no releases anymore. But there are releases of MUMPs.
No, it's now called M, and
yeah.
The major commercial
yeah. Yes, MUMPs is still around. And also, and Cache is a direct descendant of PIC. Right. So, and Cache is under heavy use in development.
Cache is MUMPs, not PIC. You said PIC.
Yeah.
Not MUMPs. Cache is MUMPs.
Yeah? Okay.
Right.
So, anyway, but we had a few sort of different kinds of databases, and they sort of got used concurrently, and then in our sort of period here of 1995 to, we'll call it, through like the mid to late 90s, there was a sort of period where nobody was doing anything other than a relational database, at least as far as I can tell, in terms of anything new. Yeah?
No, you had the object relational database development going on there too.
Yeah. But the ones that worked were actually more relational than object. Yeah, and we had a brief. We actually had a brief flurry. This actually goes sort of through 2002. We had a brief flurry in the early years of so this is mostly relational. With XMLDB, which was launched to great sort of fanfare. Yeah, which was launched to great fanfare and a lot of hype and the death of relational databases and all this thing, and then the XML databases settled out into this small, profitable but small niche in the industry. Where they've sort of remained since then. Although the side effect that we got of that was, and this was something that I don't know so much about in the early years, the side effect we got of that was hybridization, where you know, a bunch of relational databases decided, well, hey, we can support XML. It's not that hard. And then starting, depending on who you look at, but starting somewhere early in the 21st century, we suddenly get this explosion of different types of databases. So we've got, so let me actually go here. Where is this? And so we've got, we're adding into, you know, here we've got a whole bunch of new key value databases in the embedded space. And we've got streaming, and we've got, let's see what else came up there. Your column store, and graph, and a resurgence of document databases, which came back strong and that sort of thing. Well, that's not really a type of database.
It's really fundamental to how you interact with it and how that database is implemented.
When you take a relational database and start shutting the computer back into a key value database.
Well, it's more like a I think it's more like a document store with joins inside a document. Because you'll have access to everything that's hanging off of your shard key. And you can hang a lot of stuff on that, and you can do joins.
Yep.
It doesn't become key value because you can also do multi-partition joins on shard keys.
Yeah, but from that respect, we have to like distinguish the clustered C-store databases from the non-clustered ones, and then it gets very, you know, and
taxonomy is actually not all that interesting.
Yeah. And what else do we have? When they first introduced Mongo, I thought they were actually doing a hierarchical database, which I was fairly interested in. No, it's more of a document database. I got a prospectus from a company that had dug up an old network database from like 1978 and was trying to reestablish it as the hot new thing. So we've had this sort of resurgence of all kinds of things, and this is one way to sort of look at the database space that's going on. And if we look at it this way from specific types of technologies, the actually interesting thing is that we've had a huge resurgence in the number of databases, and the number of open source databases available in particular, but all kinds of different databases in a way that we really haven't seen since in the early 90s. We had, for example, particularly lots of new relational databases. Like when I was choosing, I remember choosing a relational database for a client, for an SQL database for a client in like 1995. And this was pre-knowing about, you know, and lots of little companies selling. I remember I was able to, even narrowing it down to the feasible choices, I was able to present the client with like 6 different choices, and I had to look at like 20 different database systems. So, and now we're mostly seeing most of the innovation in some of these other areas, but a whole bunch of things. But it's actually interesting that a lot of this has been fueled by a very limited number of advances in technology. Is that basically what we had in 2000 was, these are fun, I like these. So,
I think part of what happened is once we had something, once it was okay to talk about something other than a relational database, it also became accepted to start talking about lots of different kinds of storage models, and that's why the explosion.
Yeah. Well, and bizarrely enough, one of the things that fed into this was the acquisition of MySQL. Because suddenly with Sun's billion-dollar acquisition of MySQL, getting money for a database startup became a heck of a lot easier.
So it's also very much driven by improvements in hardware.
Yes. Yeah.
I would say a lot of that dates back to Ledger. It's the nucleus of a high-speed key value store.
Yeah.
It's not Brad's hack for trying for money pictures.
Yeah, but like in advances in database technology specifically, The last like sort of major things that we saw actually all happened to pop up in 2000. One of them was the original C-Store paper. Another one was MapReduce. See, I don't include CAP in that because CAP was just a theory to explain something that a lot of people knew anyway and didn't have words for. And it's more of a...
We knew it anyway, but once we had the words for it, CAP is starting to, is influencing the design of database and the funding of databases.
Right.
Yeah.
But the problem with CAP is that it's so high level that it really fails to describe the actual trade-offs made by individual databases. Like you can't say it's CA or AP because they're A and P are really...
CAP is not useful for implementers, CAP is useful for funders.
Yeah. So, I'm spacing now. There's a third thing that originally came out in 2000. That's now.
I'm curious about the MapReduce.
So what MapReduce basically did, and this is why it's actually a big deal, is it took something that was available in very expensive proprietary databases, namely clustered parallel query, and made a lightweight but nevertheless adequate form of it available.
So basically what thing is the concept is there is that this gets exposed in a way that people
Could use it.
could use it.
Yeah, whereas previously you had to fork out $1 million for a Teradata system or $300,000 for a Greenplum system or whatever to have access to this kind of parallel query.
Because it's actually been done for a very, very long time.
Yeah.
Oh, it goes all the way back to it's MapReduce is theoretical computer science. It falls right out of the land of calculus.
Yeah.
We've been under that since the late 50s.
But MapReduce provides the plumbing to do that in a roughly ad hoc fashion. Create your own custom query.
But, so, I've started thinking about, where, because there's all this change going on, and because we look at all the databases that are now available, and it's pretty clear, and if the history actually taught us anything, because we particularly go back, like I said, we go back to, 1995, and I'm doing this examination for clients, and there's all of these SQL databases, like some of the ones we looked at were let's see, OpenBase. Like two of the ones I looked at were actually called OpenBase and FreeBase. An unfortunate name if you really think about it. Which was amusing because this one was not open source and this one was not free. But those were two, they had a sort of small business disorder, a bunch of SQL, that were sort of a work group scale. Obviously, Interbase back then.
Well, weren't they all just basically network versions of the old DBase concept?
No, because they were SQL. But anyway, so you look at this, if you look at the number of SQL databases that were available in 1995, they're actually a lot less now. Most of these from perspective, Interbase sort of survived this fire. But like these companies don't exist anymore. And their code base is gone. I don't think it had much of anything valuable anyway. So except maybe to database students it was available. So it's pretty clear that if we're looking, say, 10 years from now, most of the new databases that we're seeing now will not be around. And some of the old databases will not be around in forms that we're familiar with them.
I'm pretty sure even the ones that do stick around, so the APIs, the storage, and the internal code,
Right.
10 years will be radically different from what it is right now. It's going to be a different database.
So, yeah?
I think a lot of those littler companies got wiped out by the open source databases. So, effectively, you had a lot of these niche players, and then with MySQL and Postgres effectively being free, it was virtually impossible for these people to catch up, and they all just disappeared. But the larger question is, in 5 years, you aren't going to have the same case where these can't succeed because there's open source available. they all are gonna be open source, well, they're all
Yeah.
open source now.
These guys could get wiped out by MySQL or Postgres. It's too early for that. These guys got wiped out by Oracle and Sybase and
Okay.
Microsoft SQL
No,
Server.
some of them actually, when I saw OpenBase, like OpenBase, for example,
So,
continued to
yeah.
have a user
Big
base
commercial guys.
up to about 2,000. But particularly MySQL, because particularly they were actually, because one of the things is, if you remember in the early, one of the great things about MySQL coming on the scenes at the time, our choices for a database to back a website were, actually the only affordable database to back a website that we had was FileMaker.
Mhm.
About that time, the 90s, your choices for databases were FlatFile, Oracle,
Yeah, oh yeah, I learned flat file CGI.
Because there was Oracle, it was Sybase and Oracle, because it was
Yeah.
Oracle and Cyperl, which was before
Yeah.
modules and before the DBI.
Right. So we obviously we can't predict what new technological stuff people are going to come up with, because if anybody here knows, they're probably under NDA prevented from talking about it. It would be fun to actually have a session. I don't feel like I have the knowledge to actually, maybe some of the MIT people can talk about stuff that people are inventing with database technology right now that they think is going to be big in the future. But I was actually thinking about this more from a perspective of what do people want out of the database.
I think you also have to think about a few different categories that we've described. Data model, like relational graph,
Yeah.
hierarchical, whatever. But there's also, what we allow for constraints. Getting back a little bit into the cat term, it's not defining necessarily the data model in any way, but what we can accept for constraints, like certain databases that need immediate consistency probably are going to start going away more and more as we have databases on every single device in our life, and they're not going to be perfectly in sync with everything else. Seeing things like TouchDB on every phone now, and having that loose consistency model that it can sync up later. I see that being a way that we start heading forward.
Control synchronization can be more important than perfect consistency. Or at least what I want.
Yes, on your personal devices and on all this type of stuff, but the core places where you need, where the relational databases are, where you need absolute consistency, that doesn't go away. The banks aren't going anywhere.
So I like invoking the one time that I ever touched like in a financial application, and there was nothing that looked like a SQL database transaction.
Right. No, it's not. But the point is, you have that area will be bigger in 2020 than it is now. Will just be dwarfed by everything else. So
It might be more distributed though.
I think what it
Maybe.
is,
probably not.
we're going to have, what's going to happen is we'll just get more and more applications and uses where developers will just get used to the fact that they cannot pretend to see the entire universe in one moment at any time.
Well, the thing is though that there are applications that require absolute consistency within the domain. For example, if you're selling seats at the opera, you can't sell the same seat twice, and you can't, for that matter, tell somebody that they purchased a seat and then call them back 2 hours later and say, oh, we actually sold that to someone else.
But
That's not
acceptable.
acceptable.
Opera House has at most 10,000 seats.
Right, but there's plenty of other examples of that. For example, selling seats on the airplane.
Except those you can make.
Except that, yeah, well, that's true. The airlines have sometimes made us accept the reassignment, but people are not happy about it.
You cannot allow eventual consistency in an accounting system where money is insured. And those systems are going to need to be there.
It just,
So,
money's always involved, it depends on how much it costs to fix it, right?
No,
So the
in
stock
those
exchanges,
systems,
the stock exchanges, as they
you
are
can't
now,
allow
they
that
don't have
in your
perfect
designs.
control.
Things would break anyway. That's,
They did not on that.
Well, it's possible.
It's not possible, but it turns out that you can still run a market exchange system without a perfect universal view of the market.
Yeah, but I mean, even traditional banking systems, you still write a check, that's measured consistency. An ATM card, there's a reason why there's a $300 limit, and that's how much trust you have, because there may not be immediate consistency with what's actually in your account. That's why every night at midnight, things finally sink and.
Checks may go away. Checks are gonna go away.
Well,
Don't
yeah.
count on it.
But still, that model, I
But
mean, even
the
if you
point-
use the same model.
The
it's
point
a
is
little
that,
more.
the point is with the bank system, what's available in your account is a well-defined quantity.
No, it's not, really.
Yes, it is. It's what's available in your account. There may be checks out which haven't made it to the bank, and you may be able to withdraw them there. But the bank has a single number.
But
You
you
know,
can
so
use
it's-
it
I- I-
until they get the number.
You can overdraw.
You overdraw.
You can
you get
overdraw,
a
but
fee.
what's available in your account.
I disagree. If you sit and calculate the balance in your bank account in a given moment, you actually have to be in the future from that moment and have gathered in enough stuff in the light cone of possible events to compute what, at this moment in the past, the balance was as if it was this amount. And the banking network is fast enough that you can easily compute it 24 hours in the past, and you have a pretty good chance of computing it 8 hours ago. But
Well, there's another way to actually look at databases that's a little bit more 10,000 feet. Because, and I like that because it's a little bit easier to make predictions. Mainly, what are people using databases for? Because there's a lot of sort of different things, because we can go this sort of thing with consistency and stuff, but a lot of it comes down to the sort of what is it that people actually want out of it? What's the value of having a database? And one of the things I look at is, as obviously we mentioned already, and this is going to be, in terms of numbers, going to continue, wait a minute, I'm misspelling that horribly.
We're going to create a new
Yeah.
amendment.
Is this space.
SQLite destroyed a $10 million industry and replaced it with a $100,000 company.
Yeah. Well, and this is just what I'm saying growing is that, obviously we've got, not just SQLite, now the Couch is getting, heavily in the embedded space and a bunch of other databases, yeah?
Lots and lots of storage, searching through that.
Mm-hmm.
Switch algorithms.
Yeah. So you're talking about our big sort of, yep. So then we have our, because we have on the other end from the embedded thing is we have giant big databases that just seem to be getting bigger. It's actually into a couple of different areas. One of them is analytics, and that's a traditional area. I see it shrinking. I see it actually going up. Because now that people can afford the storage hardware to store petabytes of data, they want to store petabytes of data.
More data and more types than we
Yeah.
ever stored.
And you can throw mixes out of this, and you can.
Mm-hmm.
And part of the reason the analytics stick around is that our first knee-jerk answer is why don't we throw this out of the data away? So we're storing it. And now storing petabytes of data is expensive, and so you have to cost justify while you're storing that data, so you need the analytics.
Yeah. The other thing that I've actually seen is an interesting growth in the big data area, which is a fairly specialized use, but it's become so common as to be consumer hardware that I actually sort of have to include it as talking about this. In an area actually particularly where I don't know databases that address the specific area is what I call write once, read never.
I call that legal storage.
Yes, and that's exactly what's fueling it.
Mhm.
But the thing is, we've got anti-terrorism, we've got SOX, we've got HIPAA, we've got a bunch of other things.
They have the SEC storage requirements go all the way back to the 80s. You must have this, and there's a standard form for retrieving it, but it's almost never invoked.
So let's sort of write once, read, and see.
Yes.
Right once, read when the agency suggests it.
Yeah. Yeah. So, and the thing is that even when you have like this write once, read never, or actually what's the more interesting case, because it's a slightly broader case in the industry, because the thing is that with the regular analytics thing, you're making the assumption that you're going to store a bunch of data and you actually are going to run reports on pretty much all of it, at least on a summary basis. But then we have this other case where I actually want to go, it would be write once, read seldom. Or read, read a small portion.
Right once, read roll up.
No, because this is not, because the analytics is the roll-up. The analytics is the roll-up, but here's the other case I'm seeing, like, for example, I'm right now working on a project with Mozilla where they are they want to actually store and instantly process all of the crash reports that they get, which is actually in a rather startling number on a per-hour basis. And so they really need a database that allows them to insert these things in a non-blocking way at an extremely high rate of speed, and then run individual sort of searches on them where they're actually probably never going to touch most of the data, but they don't know in advance which portions of the data they want to look at. And that's a case that I encounter a lot, and it's actually very similar to the case of these regulatory databases. And one I feel is actually not currently addressed by anybody, that any of the databases that I know of. Can you say something else?
Well, large energy companies are just compiling data because a lot of buildings are having a lot of smart circuits installed. So it's a lot of that same type of data that might be useful, but maybe might not be. It's a lot of records with small data fields.
Power generation distribution combines the very worst of high-speed scientific data with the very worst of legal analytics.
Yeah.
Because it's a large, ancient system that you need to get real-time data from, you also want to do analytics from, and the investigators, regulators, and auditors want to see it too.
Yeah.
I don't see how analytics doesn't disturb write once, read never, because a good analytics system will have good compression in order to speed up queries. So
Right, so there's two differences here,
yeah.
which have to do with the use case. One difference is, often what you're doing with these is you're searching for individual pieces of data, and not trying to run big aggregates. So they don't need the machinery to run big aggregates.
It's true.
The second, and here's the really second big issue that's been a problem. I mean, in theory, you could actually construct one database and serve both of these. I just haven't seen it. Is that one of the things that we generally do with the analytics databases to optimize them is that their data input is batch processing only. And the problem with these systems is they're almost always receiving data in a continuous stream of very small events.
There's no difference to all these systems. A large portion of the data is typically completely offline.
Yeah.
Yeah. So there are analytic systems that are append only and occasionally merge stuff. So it's all sequential I/O. So they'll work with continuous stream.
Yeah.
And when it comes to reading one record, you're right, it's going to be slow because you're going to have to probably do, I think, a binary search through all the segments. But how much of that and how often, if it's rare, maybe you don't care about terribly.
Yeah, it's just, I mean, part of it I started thinking is different is because most of the activities in the analytics sphere is in C-store.
Yeah.
Is C-store databases, and C-store databases are terrible for this.
I guess I don't.
Because they're really bad at single row inserts.
Oh, so.
And getting a bunch of single row,
Yeah.
individually committed single row inserts from a wide variety of sources.
Why would you commit them in? Why would you just batch them? I guess.
Right, well, because then you have to add you're going to have to add a lot of middleware software to handle the batching and that sort of thing.
So I can see an analytics system having a front end that
Right.
optimize that. So
Well, and that's what people are doing now.
Yeah.
But what I'm saying is they're not happy about that.
yeah,
They'd like the software to just handle that for them.
I see that.
So, and I'm just saying that it represents a distinct use case from the traditional analytics BI use case. So what other use cases do we have that we would expect to be around in maybe even bigger 10 years from now?
More streaming, real-time decision, real-time
Ah,
automated
okay,
decisions,
right.
streaming. Both financials and power distribution are kind of on the, we'll split it into, it's not so much on that problem.
Yeah.
Surveillance data, because,
What?
eventually somebody wants to go back in time and find out who did it.
Well, that's the right one, so we never, that's the
Yeah.
data storage.
Well, but except that the difference is, there's just a big difference in storing video from storing the other stuff and having somewhere to search that.
You don't actually have to raise your hand, you just speak up.
I was gonna just say search, I mean,
What?
I don't know if you'd include under real-time decision, but search is another one.
Yeah.
It's kind of a combo of
Yeah, so search is big data.
So real-time decision is, what I've seen in the stream presentations is you have this, this painful tension between making decisions based on instantaneous data and decisions based on the accumulated knowledge of the incoming stream.
So,
I think another one, getting back more to like consumer spaces, you know, with all the various cloud trends going on, the database as a service, you know, like
DBA was versus.
yeah.
So
Basically, there's a service out there that I just point my app to, and magic happens. Like I don't need the DBA anymore.
DBA is somebody else.
Yeah.
Because the DBA has even less ability to get online application.
But
yes.
it's not the same as big data because it's not like one giant chunk of data.
oh,
It's
yeah,
a
so
lot of
we're
data,
talking
lots
particularly
of little-
multi-tenant here.
Yeah, lots of little data, which is different than one big wall.
Yeah, and so I would actually say that both of these are part of a slightly larger class. So the larger class I would say for search is this actually falls into a large class that I actually call cache DB, where you have this particular use case that involves your primary goal is to support very large numbers of reads. Your secondary goal is to support very large numbers of small writes. And you're willing to sacrifice things like consistency and durability and, you know, and absolute certainty to some degree to actually get those. Compared to your sort of opposite thing that we have here, where this is going to often be, I mean, sometimes you use like a cache DB class for this, because we also have this slightly different, is that we still have a desire to do transaction processing. And I think a lot of the transaction processing, though, is going to, that's where we've already seen activity in the various cap theory databases, is that having a defined trade-off of availability and consistency and durability and other things in order to deliver certain targets that generally involve a large number of writes. And a large number of writes that have to complete, which is why it's different from the cache DB case.
An interesting case I've seen is a large number of writes, most of which have to complete. This is something that shows up a lot in gamer work in the networking systems.
So, what are the use cases do we have? Some sort of major use cases. Anyone?
What about, this is an offshoot of use cases, but what about changes in hardware, like people wanting to use things like
Oh, so that's, yeah, so let's take a new chalkboard, because we have all these chalkboards.
So my overall arching grouping thing for new hardware is in the past we had memory and we had memory and we had tapes, and then we'd have tapes and disks and memory, and now we can register and cache and memory and disk caches and disks and tapes. And all that happens is we have new hardware, and we never get rid of any of
the old hardware.
The existing systems get faster. We just keep adding more and more stacks of things between extremely expensive, extremely fast, extremely small, and very large, very durable, and less expensive. It's
Adding more layers to the pyramid.
adding more layers. The pyramid of storage gets higher and higher, but we never actually take any of it out.
Last year at the New England Database Day, one guy presented something called phase change memory, which is basically durable RAM. So in theory, we could get a holy grail like that.
I suspect that if you go to start with, knowing nothing about it, but I learned about that when we work out the economics of manufacturing, you'll slot in at the speed cost variability above or below flash someplace, and if it takes off. The only times I've ever heard of a memory is the only memory systems that we have ever got rid of in the history of computers, and they're not even really got rid of, as real edge cases, are paper taping cards, mercury delay lines, and be much hyped and on core memory. And even they still have use cases in weird environments.
Well, if you include metal ribbon, we haven't gotten rid of the paper tape concept.
The amazing thing about core is core was persistent in memory.
Core still exists because core works in hard radiation environments. So it's used for space, nuclear, that sort of radiation.
When the memory was core memory, the computer went down, the memory was still there.
Yeah, that was way back when we had 2 layers. We had the core memory and the mercury delay lines and the balance. So we had 3 layers.
Mercury delay, I don't think mercury delay lines in core
Yeah, that's
cohabited.
Oh.
Mercury delay
Yep.
lines were.
So does anybody see anything, I mean, so that's a question, does anybody think that we're going to get hardware advances that are going to change things enough that we'll need new types of databases?
I think it go the reverse at some point. This was tried in the past and might be done again. At some point, they try to take some of the database functionality and put it in silicon, which can result in a very great speed up in that particular process.
I think that we will always, the fundamentals are that there will be locality in our storage systems, right? That's, speed of light issues and so forth tell us there will be locality, there will be caches, there will be, the software better exhibit temporal and spatial locality in order to use those systems.
Yeah, I like the network databases and clean up people. Even if we have gigabit and 100 gigabit Ethernet, the thing that kills you on network databases is not the throughput, but your latency. So that's locality.
And that drives me crazy that, you can have a situation where the speed of light delay across a room is only 30 nanoseconds, but it takes a millisecond to get a message from here to there. It's five orders of, no, well, the marshalling, unmarshalling isn't such a big deal. It's going
Yeah.
through.
So why are the network people always just focusing on improving throughput?
Because that's the one that they can still fix.
Yeah.
Ethernet's now run at, until there's a major breakthrough in material science, the speed of radio waves down a twisted pair or the speed of light in fiber are not going to change.
Yeah, but that's not the dominant cost of network delay. It's inside a room. From here to California, yeah, but from here
Inside the
to.
room, I'm willing to guess it's just the process. It's
It's the 7-layer stack.
It's the cost of the context switch from user space to kernel space and down into.
So there are networks where you don't have to, where you can send a message from user space, right?
Yeah, zero copy systems.
So
which
there
you
are-
can see in POSIX.
Well, if you're doing-
POSIX machining.
But even those systems suffer from,
How
10 microsecond latencies.
are you talking about an optical transfer of the data, or are you talking about electronic? Because
It doesn't matter whether you send bits down a wire or down a fiber to first
No,
order.
but if you're sending it,
Because you get within a factor of 2 of the speed of light.
yeah, but you've got a significant interface and conversion from optical to electronic.
But it's not, even optical to electronic is not microseconds. That's a few nanoseconds to do that, so.
Because that was what was, without much of a guess, the problem was the actual electronics of getting the representation of bits into the transceiver hardware.
It's getting the bits from the registers in the processor out through the North Bridge and across this and over to the PCI, and then that's the thing.
We keep having this cycle of reincarnation where people complain about that, and then so they design a whole new CPU bus to pull it all back in. And then 3 more generations of CPU Speedway, we now have our new fast bus that will solve everything is now 3 layers away from the CPU again.
Yeah.
Plus we have the old ones that we had the previous generations.
Well, so when you try to figure out where what the costs are, if you look at something like the recent multi-socket chips, where they actually are sending messages some distance, right? The fact that it's only this far doesn't really matter. They can actually send messages to each other in tens of nanoseconds, right? For the memory coherency. So, and so you can do a load and and only tens of nanoseconds later you can get the data back, which is only hundreds of missed instruction opportunities. Right?
Isn't there, even if you send it from user space, at the point that you send it, usually that process will still sleep, waiting for the response, or be swapped out.
No.
If you have a busy system, there's other things that want to run, they'll swap it at that point.
Right.
No, so the user space messaging systems, you send the message, there's no context switching or anything. It's up to you to do the polling. Things like InfiniBand have support for this kind of thing too. You don't have to take the microsecond system call. But the system call doesn't explain it either, because the system call is only a microsecond, and you see, you'll see millisecond. You know, so here's another data point. If you get a battery backup RAID, you can only do 3,000 f-syncs per second.
Because it keeps the buffer.
And that's memory to memory only, right? It's memory only, but it's going through the PCI bus and all this stuff. So somehow that path is 300 microseconds instead of what, it's only this far, it should be, a microsecond I could understand.
The PCI bus suffers from some of the same limitations that the old thick wire and thin wire had, is that it had it had definitions of how long the bus could be, and so the standards and the chips have timers in them waiting for reflections to die out.
So I want to float a couple more use cases past people to see whether or not they think these are significant use cases. This might be a use case in its own, or it might actually be a branch of analytics, which is inference.
Is that where you don't even know what question you want to ask?
Yeah, so I'm going to give you, and this is what the whole, semantic, and RDF stuff is about, right? Which is,
People want that shit.
is to say, I'm going to give the system a whole ton of data, and I want the system to tell me which data is significant.
What things are true?
Yeah.
Just what things are interesting.
What things are interesting, yeah.
That can help.
So in other words, I'm going to give you an example of like in practice, the semantic web people like to talk about the web thing and that sort of thing. I don't understand what they want to use the inference for, but I can understand things that I would want to use the inference for. Like for example, imagine that what you're loading up is actually is actually monitoring data from a large network, security traffic. And I want the inference engine to actually tell me when somebody is behaving oddly in the network. And I can't in advance give it a definition of what oddly means.
You just have to give a set of rules for constructing the rules for what normal traffic looks like. Another similar situation is one that shows up, starting to show up both in physics and pharmacology now. It's an interesting problem, both database and math, where you have 1 billion variables and you don't know which ones are correlated. That's an interesting database problem and a different statistics problem.
So I guess the question to ask for people is do people actually think, first of all, do people think, I tend to think that right now this is not a significant use case because the software isn't good enough for it to be useful.
I can see network people doing that, and also
But
safety is, that one starts you into real-time decisions as well, because a lot of the inference stuff, people are interested in inference on real-time data, like network monitoring logs, or once again,
I think it's going to be huge in medicine, which medicines interact with each other and those kind of things.
Yeah.
But also,
Now you're not just recommending like Jesus on Pandora.
yeah.
Right, don't credit card companies use that for fraud detection right now? They actually use some sort of thing like an anomaly pop-up, which the system detects.
And the other actual use case that I had thought was strictly an own use case, this is like our use case, actually honestly our main use case for Postgres as a database is becoming database as a platform. Because the database is actually not just a database but an application server. Now I know that was more of a legacy use case from like Postgres and Oracle and older databases, but I've gotten a little bit involved with Couch. And what are people excited about in Couch? You need something called Couch App, where you have a couch database that serves up application code that is then run.
This gets back into the locality issue.
Yeah.
We have had for decades this horrible tension between we want our programs close to be as possible, but what is the hardest part of your stack and scale? Database core.
Yeah. So, so in other words, so that's actually sort of making me inclined to think that this particular use case is not actually purely a legacy use case. That there is ongoing demand for it if we're having a 2-year-old database suddenly getting used for that purpose.
It's once again, real-time decision, your decision rules have to be as close to the stream as possible.
Also putting an HTTP interface on a database, it's a perfect place to store your code.
Right. Yes.
And then once it goes all the way back to theoretical computer science, and then code is data. If we keep our programs in a database, we can run them there too, right?
Or otherwise.
Right.
Yeah, go back 30, 40 years, systems did that.
That's the way you do this.
What, keeping our code in our memory system?
No, you store your code inside your database.
Word MIT doesn't support that. That's
So-
up at Harvard, you can't put your code in your, same space as your
I
data.
think the platform definitely gets into the database as a service too, because also the platform as a service, how, like Heroku, for example, how integrated it made everything. So you just push code and your database and everything's taken care of for you.
Oh, right. So the platform is in some ways actually connected to this. Yeah.
So you earlier asked, do you think changes in hardware change types of database?
Yeah.
And I think we're going through one of those right now. That's how MapReduce became possible. And it's not a change we didn't need to match a kind of hardware. It's just that it happened once we hit a particular economic cost point for large quantities of hardware. It became possible.
The thing is, if you look at the rise of the relational database, the rise of relational database is very tied to the rise of the Intel server. Because in the mid-90s, you had this circumstance where companies could afford their own database server, which is not true in 1985 unless you were the federal government or like yeah, some humongous company, so you could afford your own database server, but you could generally only afford 1 or 2 of them. And so you needed a database that you could run on the database server that would be able to do everything, even if it didn't do a bunch of it particularly well. Well, so now, what we've already had a fundamental change in the hardware is that it is now everybody's carrying around a machine capable of being a database server in their pocket.
Another thing that happened though is that our demands for what we want these machines to do have grown faster than, as fast as they're meeting our desires for them to be faster. And so we no longer can be content with the one tool that does everything kind of okay. So we now have the economic demand on, we want this tool that solves this problem and then others. And we can afford to have that specialized tool.
Well, my attitude is that people always wanted that specialized tool. It just wasn't economically viable because you had to use the company database server, and the company database server wasn't capable of running more than one database at a time. Now I can have 3 versions of Postgres and Couch and MySQL running concurrently on my laptop.
Specifically tuned for different applications.
Yeah. So I think that's actually resulted in a lot of explosion of different kinds of stuff.
And it also changes the economics because you have orders of magnitude more of these things out there. So companies that are trying to make a living on this have an enormously bigger market.
Yeah.
You have more development.
Right. So here's a question. Does anybody have any reason to believe that the database market is going to shrink or flatten out in the next 10 years?
It may change names.
Approximately.
Yeah, well, there's a definitional issue, because one of the questions that I love bringing up is today, what is the definitional difference between a database and a file system?
Pretty speaking on
Yeah.
POSIX or SQL.
Yeah.
It's
Or even like a smart spreadsheet.
Yeah,
A lot of people use this things to store all their little things, and secretaries use it
Oh.
to store all their stuff in their office.
Also,
So I think there was an effort by, one of the people by Amazon to offer a easy database for people.
Google.
Yeah.
Is it like a cloud service or something?
yeah, well, there's a lot of that. And actually, that's my joke, is like people say, you know, what's the most popular database in corporate America? And my answer is often Microsoft Excel.
Yeah.
They use it they use it both literally as a database, and then also it gets back into the locality thing. It's their data is in an Excel spreadsheet, and their code is in an Excel spreadsheet, and it's in binary form, and it's not in configuration control.
Yep.
Of course, probably the second most popular database in corporate is probably Microsoft Word.
Yep.
It's the other place.
Which leads back to complicated file files.
Yep.
So wouldn't you think that's a big market for those types of people?
The problem with addressing that as a market is that very, almost, is my hope and my perception, almost never does a company decide to bet its line of business on people's income Excel spreadsheets. It's just the barrier to entry to starting a spreadsheet is so low that it bubbles up.
Yeah, but I think actually that does play into two areas that we've already defined here. One is the embedded data space, because people will get the smart idea of having a spreadsheet interface that's backed by a database that is capable of synchronization with an actual database.
Because even in the mid-'80s, there were a bunch of companies, several companies competing against both 123 and eBay's, that their big breakthrough was it was actually the same
Well,
application.
Most people are unaware that actually currently both Excel and OpenOffice have the ability to do direct synchronization to a database. This is what people just don't use it.
Well, but I think the turning point right now with the Excel world is Google gives multiple people to access the same Excel spreadsheet at the same time, so now
Right.
we need some
Yeah.
sort of.
Yeah, and so this is where I think we're going to see the big growth from that particular user base.
There's another
Yes.
dimension to this, and that is that more and more the people that used to do these things in spreadsheets now have applications to do the same thing, right? To keep track of my music, to keep track of my photos, all those kind of things. So that splinters again into all kinds of app-delivered capabilities.
So that just reminds me, we have an elephant in the room we have been ignoring is multimedia data. The world is now being, people are being buried in digital photographs, videos, all these sensors. Is the whole a lot of the big data issue now. It's we are often still kind of stuck back in the flat file days of storing multimedia data. Sports Illustrated makes most of their money now not on selling their magazine, but they were the first major media property to switch almost entirely over to digital photography. And there was no digital asset manager for their use case. So they spent large amounts of money writing an enterprise-scale digital asset manager for photographs and media, and they now make most of their money licensing that product to other magazines.
Right. So the question is, does that actually require, that is it's a different use case. Does it require different database technology?
That probably doesn't. But when you want to start searching on things,
We want to search it.
within the images, with the videos.
So you already have enough
Database.
content manager products out there in some ways, right? So
Yes, but none of them are, all of them are very large, very expensive. None of them are open source. I have family in the industry, so I can see the inside. It's part of what is the embedded advantages that both Pixar, Mouse, and DreamWorks have is their skills in managing this data and the content management systems that they have built to manage these movies that they make, and how they can get 1,000 animators all working on these ultimately hundreds of thousands of still images, all carefully cataloged, logged, color tag. They're all in configuration management, and these are systems that cost, inflation adjusted, what RDBSs cost corporations 20 years ago. And it's not, and very quickly going to reach the point where not just the few big media companies want that. We all now have digital cameras. We're all going to get more multimedia sources. We're all going to want to source, manage, access, keep all that. Companies are going to want that. And I think it's a different level probably than what you described so far.
Does anybody have other comments or feedback? Yeah, we're at the end of our day here.
I just have one question.
Then we go talk.
One question on
Yeah.
where these are heading. One of the things I would like to see is I would like to see a lot more self-tuning and a lot less knobs that you can twiddle in databases.
Yeah,
It
it's-
disappears.
That's actually dynamic tension, and it's the same set of dynamic tension driving, say, the PC industry. Because one of the problems is, people ask all the time, why haven't desktop PCs become easier to use? Because they haven't become a little bit easier to use, but they haven't become substantially easier to use over the last 15 years. It's still the case that my in-laws, for example, call me for tech support all the time. And the answer is that the industry is often driven by its cutting-edge users, because they're the ones with the most money that they're willing to spend on the products. And so making stuff simple and easy to use and standardized tends to lag.
So,
But it's a somewhat different thing, because if you look, for instance, if you look at Oracle, which has 6 trillion knobs to tune, and then some of the other ones which were probably architected later when people understood things better, they realized that no human being can actually tune those things.
Right.
And so they say, but the computer can, and so those become self-tuning internal type things.
or
So
there
we'd
are
like to see
third-party products that too.
Yeah.
secondary.
I think that's actually what I mean, approaching it from a realism perspective, I think what will happen is the management tools will get better rather than the core databases getting better.
The problem with auto-tuning is that even given the assumption that the application load is reasonably predictable and constant, an application load will suddenly spring things on us, and we're running the same well-defined database, the same well-defined application, we're going through, and yet we upgrade our database servers and expand our cluster every year.
Well, Tuesday needs to go. We should go upstairs, I guess. So let's finish this up, and some of us will continue discussing this, but thank you very much.